Okay, so for today we're going to go over probably the second most important concept in like mechanical or classical physics. Okay, that is Newton's second law, right? And it is hugely important because it governs the movement of a lot of things. Okay, it is going to deal with the situations that Newton's first law does not. Okay, we learned that Newton's first law deals with any situation where all the forces are balanced and there is no net force. Okay, situations where Newton's first law applies involve objects that are not moving or objects that are traveling at a constant velocity. Newton's second law deals with all the situations where there is a net force or an unbalanced force, and thus the objects will always be accelerating. Okay? Does that mean they have to be going faster or slower? Think about the definition of acceleration. It's any change in velocity. It's velocity of vector quantity. Okay, so if I'm just walking along, okay, at 1 meter per second, and I do this, and I continue to walk at 1 meter per second, did I still accelerate? I did, because I changed direction. Velocity is vector. If I change anything about my velocity, it doesn't have to be the magnitude, it still requires a force. Okay, because believe it or not, I did accelerate right there. Okay, and I accelerated because when I turned this corner, I changed the direction I was exerting a force in. I started pushing a little bit that way so that I would turn. Okay, I shifted my weight, okay, and there was a component of my force that pushed me in this direction. All right, so any change in velocity could mean that you only change the direction in which you're traveling. Okay? Most of the time, for our purposes, it's also going to mean that the magnitude changes as well. Okay? But I don't want you to think that that's the only situation in which an acceleration is occurring or that a force is required. A force is required to change direction. Okay? You don't just magically turn. You have to have something push or pull you in a different direction in order to turn. Does that make sense? Okay, so what we're going to learn today is the relationship between force, mass, and acceleration. Okay, that is the basis for Newton's second law. Newton's second law goes like this. Mathematically, the net force equals the mass times the acceleration. Okay, that's one way to calculate net force. Okay. And the other way we learned yesterday. The vector sum of all forces. Okay, when we were talking about free body diagrams yesterday, we drew a vector diagram, okay, and showed which direction the net force would be acting as a result. All right, so if we're just looking at this part of the formula, okay, I said we're going to spend like 2.5 weeks on Newton's second law. And the formula isn't any more complex than V equals d over t. Why are we spending so much time on it? Seems like it should be pretty easy, right? Like F equals m times a, that seems like a pretty easy formula. It's never that easy. Okay? I mean, it is always that formula. It's always, in the end, mathematically, it's going to come down to that. It's this part. And it's not because you guys are not good at vector addition. We saw on the exam, like the best question on the exam was the vector addition question. Okay, you guys did really well on that. So take some solace in, you know how to do the vector part. The tricky part is identifying the forces and figuring out how they contribute to that vector sum. Okay, there's so much context in Newton's second law. Okay, and what we have to develop here is that thing I kind of told you would change your life. How you'd never look at the world the same way after this course. You have to look at everything from a perspective of what is making that happen, not, oh, cool. Okay, like it has to be, okay, what forces are causing that? What's making it go that way? What things are pushing and pulling? How do they interact? Okay, all of that stuff. And being able to almost visualize anything as a free body diagram in your head. Okay? That takes a while to build that skill, and that's the tricky part of Newton's second law. In the same way that drawing the diagrams for vector addition was initially the toughest part. Okay? The math was always the same. Okay? Same for this. Math is always the same. It's figuring out the context and the situations that can be tricky. All right, now if we're looking at this formula, the relationship between net force, mass, and acceleration looks like this. So, if I was, let's say, solving for acceleration, so I manipulated it to look like this. If I double my force, what will happen to my acceleration? So I keep mass the same. Let's say it's this. We'll visualize. My chair is the mass. Okay? I exert a force of, I don't know how many newtons this is. I'm just going to make up a number. It's 5 newtons. Okay? Did it accelerate very much? Okay. Now I'm going to push it with 10 newtons. What happened to the acceleration? It increased. Okay, did it double? It better have, because I just put double the number over top of the same number, right? If I had 5 over 1 and then 10 over 1, I got twice as much acceleration. So there's a linear relationship between the force exerted and the acceleration. Okay? The more force, the more the thing is going to accelerate. It kind of makes sense. The harder you push something, the faster it's going to go. Okay? The relationship between mass and acceleration is inverse. Okay, so what that means is, if I put, a couple of cinder blocks on that chair and then exerted the same amount of force, would the acceleration go up or down? It would go down, because now I'm pushing on more mass, and it's harder to accelerate more mass. I use the same force, but because the mass got bigger, the acceleration goes down. They are inversely related. Okay? All right, and then finally, we're going to look at problems related to Newton's second law. Okay, that's where we're headed today. Okay, so Newton's second law deals with what happens when there is a net force. We were just talking about that. So if I exert a force, I am going to cause the velocity of the object to change. Okay? It is either going to increase or decrease. Forces can also cause things to slow down. Okay? Inevitably, that's how brakes work. Okay? So if you're driving a car or you're riding your bike, right, and you squeeze the brakes on your bike, the little pads go in against the wheel, or if you got disc brakes, pads go against the disc, okay, and they squeeze. Okay? When they squeeze, they exert a force. That force is friction. It's just creating drag. Okay. Now, the harder you pull them, the more force they exert. Yes? Does that stop you faster? It does. I mean, assuming perfect conditions, assuming it's not slippery or anything. Okay. So the harder you push, the faster you slow down. Okay? And it's the same with the other pedal. Okay? Or if you're driving the car, it's the other pedal. Okay? The pedal on the right, okay? The harder you push it, the more force your engine exerts, the faster you accelerate. Okay? Everybody with me there? All right, so we're going to see what this looks like here. I got a video of a slap shot to kind of show you this. Okay? So the point of that video is to illustrate that the acceleration only occurs as long as the force is acting. Once that force is gone, we're back to a Newton's first law situation again. There's no net force, so there's no acceleration. So it only occurs while that force is being exerted. Once the force stops, then the acceleration also stops, or changes, okay, as the case may be. All right, everybody okay with that? All right, so that's that paragraph there at the bottom that I almost skipped. Okay, so as long as this force acts, the velocity increases. The greater the force, the greater the acceleration. Okay, and that's probably something we should underline. Okay, the greater the force, that's not what I wanted. Okay, the greater the force, the greater the acceleration, because it is directly proportional to the force. Double the force means double the acceleration. Okay, and something else that's also important, force and acceleration have the same vector. Okay, if I push on something forward, it's going to accelerate forward. Whatever direction the net force is acting is the direction of the acceleration. So, good news, once you know the vector for either one, you know the vector for the other. Okay, it's not like you have to calculate two different vectors, one for acceleration, one for net force. Okay, they will always share that vector. Okay, so in most cases, it's not going to be as simple as there's only one force, thus by default it's the net force. Life's just not that easy. Okay, so most of the time, in the situations we're going to deal with, there are going to be multiple forces acting on an object concurrently. Okay, so the sum of those forces is going to be our net force. So net force, like we said here at the beginning, I wrote this on the first slide, is the vector sum of all the forces acting on the object. Okay, and that's why we want to draw a free body diagram and then use it to get a vector diagram. Now, initially, vector diagrams probably won't be all that necessary because initially we're going to do mostly collinear vectors. But once we get to perpendicular and angled vectors or forces and things like that, then obviously that's going to come back into play doing all the tail to head stuff. Okay, so if we have this diagram here, let's say that this is the puck.
Would gravity always be a net force no matter what, or if it's a car, would you just ignore gravity because it's on the ground?
Gravity will always be there, but normal force most of the time negates it. Okay? Because gravity pulls down.
Yeah.
My car doesn't fall through the ground, right? Because the ground pushes back in response. That's a Newton's third law thing. I think actually we covered that yesterday when you were here. Okay? So yes, gravity is here. If I was drawing the diagram of the hockey puck 100% accurate, I would have to add force of gravity and normal force. The normal force is the responding force of the surface pushing back against gravity. Okay? It's why a surface can support something. There's normal force there. Okay? So the reason we don't often or always draw those two forces on is because if the surface is level, they cancel. Okay? If there are no other vertical forces, those ones cancel out. Yeah? All right, so in this situation, this is the hockey puck. Okay? We know that the hockey puck accelerated, okay, during the time when the stick was pushing on it. All right? So that would be the red force. That would be the force applied by the hockey stick. What's the blue force? Yeah, friction of some kind. Usually we add all the frictions together, air resistance and friction, like contact friction, we usually just all lump together. It's just friction. Okay. Sometimes a question will separate and it'll say F air and the other one will be like F surface, but most of the time we just say friction in total. Okay. So yeah, this would be the sum total of all the forces of friction that are acting against the puck. Okay. This would be the force of the stick. We often call that an applied force because it's the force being directly applied. Okay? And it's bigger. Okay? We can see in that free body diagram that the red force is longer than the blue force. And as a result, okay, we have a net force in a forwards direction, which is why the puck accelerated that way. Now, realistically, that red force should probably be a lot bigger. Okay? It was significantly larger than the force of friction. All right, everybody okay with that so far? Let's kind of review the diagram stuff we went over yesterday. Okay, so Newton's second law kind of goes like this. If we're talking about the effect of mass now, we've talked about the effect of force. If I double the force, I'll double the acceleration. Okay, now the effect of mass. Mass is inverse. So if I've got this guy here with his golf club, okay, and he uses it in the proper way to hit a golf ball, right? So he winds up, perfect swing, hits it as hard as he can. He will produce a massive acceleration because his force is being applied to a tiny mass. Okay? If, for whatever reason, he decides now he needs a bigger challenge, so he's going to wind up and smoke this truck, okay, with his golf club, the results are going to be considerably different. Same swing, okay? He's not changing anything. right? He's very consistent, and the force he applies through his swing is identical. But now he's hitting an enormous mass, which is going to result in an incredibly small acceleration. At which point most people go, yeah, he's not going to move that truck, Coderre. You're absolutely right. That truck is not going to accelerate as a unit, okay? I mean, unless it was on perfectly frictionless ice or something like that, then it would actually, or if it was in space, okay? Now, that would really look weird, because in space, if you hit something, it hits back, okay? In fact, it also happens here on Earth, watch. If I push on the wall, what's gonna happen to me? Stupid wall. Okay, I pushed on the wall pushed back. Okay, so if this was done in space, okay, I would hit the truck and the truck would hit back and I'd hit the truck and go and fly out the other way, okay, because my mass is a lot smaller than the truck. Okay? The forces are actually equal. It's why if you, not that anyone would do this, but if you did, if you punched somebody, okay, you could break your hand. Okay, so even if you get that punch in, you land that punch, they still hit back. Their face just hits your hand. Your hand hits their face hits your hand. Your hand's mass is considerably smaller than the mass of their head. And the bones are, smaller and more delicate, and it's highly likely that the strong bones of the skull and jaw could break the small brittle bones of your hand. Okay? So there's not a, I get to win because I punched you first. You might not. I mean, you might. If you knock him out with one punch, yes, but you might break your hand at the same time. Okay? You don't get it for free. Okay? Does that sort of make sense? Okay, so in this situation, if he hits the truck, yeah, the truck isn't going anywhere. It's not going to roll away because he hit it with a golf club. Okay? Even if it's in neutral, it's not going anywhere. Does that mean he doesn't accelerate the truck? Some people are going, yeah, the truck didn't move clear. The velocity of the truck didn't change. You're trying to mess with me. I am a little bit. Okay? If I'm standing in front of the truck and I have my hand on the truck, do I know when he hits it? Even if I've got noise canceling headphones on? How? Right. The vibration will travel through the truck. Well, that means every particle in that truck moved because it passed the vibration from one side of the truck to the other. Okay? So maybe the truck as a unit did not accelerate, but every particle that's part of its mass did. They just didn't go in the same direction. Okay? It's a vibration or a shock wave as opposed to the whole thing went. Okay? So sometimes it's not as simple as classical physics would say, well, this mass must accelerate because it was hit by this force. No, it could be different. Also, is it likely that you would put a dent in the truck? Yes. Okay, then that part of the truck moved. Okay, he changed the shape of the truck. That counts. That's an acceleration. At least part of the truck moved. Okay, it's just not always quite so simple. The stuff we're going to deal with is always going to be that mass definitely did this because. Okay. All right. All right, so when a net force acts on an object, this is Newton's second law, like written out in sentence form. When a net force acts on an object of a certain mass, the mass is always going to be in kilograms, by the way. Okay, the acceleration that results is directly proportional to the force and inversely proportional to the mass. The direction of the acceleration is the same as that of the net force. Okay, now when we calculate net force, what did I do with my pen? There it is. Okay. When we calculate net force, okay, we're multiplying mass by acceleration. That means kilograms times meters per second squared. What are the units for force? Newtons. Newtons, okay. Newtons is the kind abbreviation for the actual units for force. We just name them after Newton because, he was kind of important. He discovered a lot of things. Okay, so he got the unit named after him. Just like Joule got the units for energy named after him. Units for energy are not joules, but we just call them that. Okay, so what do I get if I multiply kilograms by meters per second squared? Newtons. Okay, yeah, I do, but what are the actual units? Newtons is just a name we give the actual units.
Kilogram times meters per second. Kilogram meter per second squared.
Yeah, it was a trick. Yeah. Your units are kilogram meters per second squared. That's a Newton. Kilogram meters per second squared. Aren't you glad we call it Newtons? It'd be a real pain in the neck to keep calling it kilogram meters per second squared all the time. Okay, so we call it Newtons. Similarly, a joule is a kilogram meter squared per second squared. Mercilessly called a joule. Mercifully, not mercilessly, mercifully called a joule. Okay, so those are the actual units, and it's important that we know that those are the actual units for Newton, or what we call the fundamental units of a Newton. All right, questions there so far? All right, so free body diagrams, we went over this yesterday. There's a right way and a wrong way. This is the wrong way. Okay? We never draw forces as though they act towards the center of the object. We draw them as though they act from the center of mass of the object. So this is the correct way to draw a free body diagram. Okay? So we would have the force of gravity, and sometimes this is called the normal force, is sometimes called the reactive force. Okay, so Fr, that would be the force of the surface pushing back. Okay. Now, free body diagrams need to also reflect scale. Okay, so when I'm drawing a free body diagram, it has to be like a vector diagram where I actually put the scale in there where it's like, okay, a 200 Newton force needs to be twice as long as a 100 Newton force. Okay, it's important that we still represent that scale in the free body diagram. These two forces are equal because the arrows have the same length. Okay, and of course, just like in vectors, the direction the arrow points needs to be indicative of the direction that force is acting. All right, I want you guys to write this one down. It's in your notes, but just write it down. It's our first Newton's second law problem. Okay, it's fairly straightforward because all the forces are collinear, but there are a bunch of forces in it. Okay, so back in the day, you used to be able to start a car, if it was a manual transmission, on compression. That means if you could push it to about 10, 15 kilometers per hour, okay, the person inside could put it in second, pop the clutch, and it would fire up. Okay, it was great if it was cold and your battery was dead, and you could still start the car that way. Can't do that with an automatic transmission, don't try it. Okay? Not only do you have to be going very fast for it to work, but you have to slam the automatic transmission from neutral to gear while the car is in motion, which is very, very bad. Okay? In a manual, you can release the clutch, and that will work, and it's a little bit different than how an automatic works. So don't try it with an automatic. You won't like the crunching sound that indicates the death of your car. Okay? All right, so in this situation, we have two people pushing this car, and there is an opposing force, friction, working against them. Okay? We want to calculate the acceleration of the car if the car's mass is 1,850 kilograms. Okay? Now, they've got this picture here. Is this a free body diagram? No, it's not. It's missing two forces. Gravity and normal force, which are going to cancel. It doesn't really say it here, but it's a level road. And we can see from the picture there's no ramp here. It's not going uphill or downhill. Okay. So our free body diagram for this question should look like this. Okay. Start out with a box. Don't have to draw a pretty picture, just a box. 1,850 kilograms. I put the mass inside. Okay. And then I draw the forces acting out from the center. Now I've got two forces going in the same direction. So I can't draw them exactly from the center, but I'm going to show which way they're going. Okay, I've got a 275 and a 395. Okay, I've got the force of friction, 560 newtons, and I would also have force of gravity and a normal force, which those lines should be way bigger than this. I've run out of room. Okay? 'Cause they're going to be really, really big forces, actually. Who remembers from yesterday how we calculate the force of gravity? I'm not that disappointed. I only went over it for like a half a second. Okay, we calculate the force of gravity by going mass times gravity. Is that mass times acceleration? But just acceleration due to gravity. It's actually how we calculate any individual force. If we know the mass of the object and the acceleration it's experiencing, we can calculate the force that produced it. Okay, so in this case, calculating the weight or the force of gravity is mass times gravity. So that'd be 1,850 times 9.81, which is going to be a gargantuan number. Okay, but do I really need it on the diagram? No. Okay, I know that these two forces are going to cancel each other out because the car isn't moving vertically. The car is moving horizontally. That means there's no net force in the vertical direction. Okay, no component in the vertical direction. So while they're there, I'm not going to include them in my vector sum. I know they cancel. I guess I am including them because I know they cancel, but I'm not going to bother writing or even calculating them because I know that. Okay. All right, so now if I want to find my net force, okay, we said there's two ways to calculate net force. Mass times acceleration and the vector sum of all forces. Can I use this way right now? I can't, can I? I'm supposed to find the acceleration. I don't know what it is. I know the mass, okay? But can I find the vector sum of all the forces right now? That I can do. Okay, I know these two cancel, so I'm taking them out, okay, and I'm going to add these ones together. So 275 plus 395 plus negative 560, or just minus 560. I just have to indicate that it's in the opposite direction. All right, so 275 plus 395 minus 560. Okay, so there is a net force of 110 newtons forwards. Okay, so now I know what m times a equals, right? Because those are the two ways I can calculate net force. This is how most, and by most I mean like 95% of Newton's second law problems go. Okay? I use one or the other. I either use m times a to get net force, or I use sum of all forces to get net force. And then I use it to get the other thing I was missing. Either one of the forces I didn't know, or the acceleration of the object. Okay? So, now that I know the net force, now I can calculate acceleration. I just need to divide both sides by mass. Okay, so 110 divided by 1,850. Is this going to be a very small acceleration? Yeah. All right, that's 6 centimeters per second squared. Okay, so every second they push the car will go 6 centimeters per second faster than the second before. They're going to be pushing this car for quite a while. Okay, I mean, if they keep pushing it, it's going to eventually add up, but it's not very fast. Okay, car's heavy, and there's considerable resistance there, 560 newtons, okay, worth of resistance to its rolling. Okay, so our final answer here would be 6.0 times 10 to the minus 2 meters per second squared. Is that answer right or wrong? I should have 3 significant digits. Okay, so I should actually have 5.94. Yep, 5.95. Okay. Okay, is that answer right? Mm-hmm. Forward. Remember, we just read that sentence that I underlined that said the acceleration and the force always share the same vector. And I always have to write it if it's a vector quantity. Okay? This car is accelerating forwards. at 5.95 times 10 to the minus 2 meters per second squared.
Are we allowed to write that answer as decimal, or does it have to be scientific notation? So it could be like 0.0595. We have to write it like.
You could write it as 0.0595 because the leading zeros are not significant digits, yeah. All right, is that making sense? Okay, so probably some of you are looking at that and going, okay, that makes sense. How is that 2.5 weeks worth of class clear? Like, well, it's 2.5 weeks worth of class because that's the simplest that it can be. Okay, those vectors were all collinear. They were all quite obvious. Okay, we didn't have to, identify any of the forces on our own. They were all clearly labeled presence. Okay, whatever. Okay, what gets more complex is in some of the contexts, okay, that we would start calculating things. Okay, so that's what we just did. All right, so this would be one where vectors would be involved, okay, where I would have to draw a vector diagram. All right, so in this situation, I've got a 15 kilogram block, and it moves on a flat, friction-free horizontal surface. Okay, so basically, it's like I'm looking down on like a sheet of ice, and the block is in the middle of the sheet of ice, and the ice is frictionless. Okay, and what's happening is this block has two forces acting on it. Okay, one of those forces, okay, is 35 newtons at an angle of 60 degrees above the x-axis. So this is kind of the free body diagram, this one on the top. Right? So if I was going to draw it the way we usually do, I'd have a block with the mass in the middle, okay, and then I would have 35 newtons, 60 degrees above the horizontal, and a second force that is 10 newtons horizontally. Okay, so just along the x-axis, so, and kind of like this. Okay, so that would be my free body diagram. If those two forces are acting on that block, is it going to accelerate? They don't cancel each other out, right? Okay, so then there's definitely a net force here. Okay, so the object's going to accelerate. We just don't know where yet. Okay, which way do we think it's going to go? Okay, I've got one force pushing it this way and one force pushing it this way. Where is it likely to go?
It's gonna go diagonally.
Yeah, diagonally, somewhere between the two, right? Closer probably to the bigger force because it's going to have more of an effect. Right? So probably, like we're guessing, somewhere along there maybe? Can I confirm that? What kind of diagram would confirm that? I just drew a free body diagram that shows two vector quantities on it. What's the next diagram I should draw? A vector diagram. I should draw those forces tail to head. Okay? If I do that, I'm going to have my 35 Newton force, 60 degrees above the horizontal, and my 10 Newton force along the x-axis, Is that about where we predicted it would go? That's why we treat all vector quantities the same. Okay? If those were two displacement vectors, if I had said it was 35 meters at 60 degrees above the horizontal and 10 meters along the horizontal, you'd have drawn that diagram right away. Okay, and it would have made total sense that the displacement would have been that exact line. It's the same for any vector quantity. If I use those two forces to push on an object, that's the way it's gonna go. It's the vector sum of those two forces. It can't help but go that way. Okay? So, is this really anything new? It's not. At least not the vector part. There's gonna be one step after I'm done this. This is gonna get me the net force. Where's the question mark? The acceleration, right. So then I'm gonna have to go back and go F equals m times a. As I said, every question we do is gonna require us to do the sum of all forces and then m times a, or m times a and then the sum of all forces. It depends what we're looking for, all right? Okay, so in this situation then, I just gotta do a vector analysis, right? I've gotta calculate my red x and red y, right? So red x is gonna be the cos of 60 degrees times 35, which is going to be 17.5. And y is going to be the sine of 60 times 35. I don't know what that is. Okay, 30.31 newtons. Okay, so this would be, well, we're just going to say that'll be positive and that'll be positive because they're both right and up. Okay, and then we've got our 10-meter vector, which only has an x component. Okay, so if we're looking at our overall triangle here, okay, x is going to be 27.5 newtons. Okay, and that'll be positive. Okay, because this x will be the 17 plus the 10, and then y will be 30.31. What do I do now? Do Pythagoras, right? This is just a vector addition question, okay? And that is always going to be the same steps. So 27.5 squared plus that number squared. Okay, so we're looking at a net force of 40.927. Newtons, and I need a vector. Okay, so for me that's going to be the 30.31 over the 27. Okay, so 47.8 degrees above x-axis. That's the only vector I was given, so that's what I have to go with. I wasn't given compass directions here. Okay. All right, so I've got my net force. I've got the vector. Question wants acceleration. What do I do next? F equals m times a. I'm going to have to manipulate it, but that's the formula I'm going to use. Okay. F net, which I just calculated, equals mass, which is 15 kilograms, times acceleration. All right, so I know 2 out of the 3 parts, so I just divide both sides by m. Acceleration is going to be 40.927 divided by 15 kilograms. So this is newtons, this is kilograms. Okay, so I have how many significant digits here? 2. 35 only has 2. So I'm looking at a final answer of 2.7 meters per second squared at 48 degrees above the x-axis. Okay, if I'm looking at the diagram I drew, that makes perfect sense. I should be going a little more than halfway up. Okay? So 2.8 meters per second squared at 48 degrees above x-axis. Okay. questions on that? So, yeah, it's a bit of like nitpicky work for sure, okay? But it isn't anything you can't do. You guys know how to do vector addition, so, okay, we just are applying it to a different situation. All right, I'm gonna give you a little break. I'm gonna try something else. Okay, so now that I calculated that acceleration, okay, it was 2.7 meters per second squared at 48 degrees above x. Okay, this would be a very logical part B to a problem like that, right? When the force begins acting on the block, it is stationary. What does that mean? Not moving, okay. So that would mean that when the acceleration is about to start, my initial velocity would be 0. Determine the displacement of the block after 8 seconds. Can I do that pretty easy? Yes. Okay. Remember that significant digit rule I was telling you about carrying an answer from part A to part B? And how we use the rounded value? Okay, so that's the one thing I would have to watch here. But I know all of this stuff, and I can do acceleration stuff because we learned that in the last unit. Okay, d equals di times t plus 1/2 at squared. That's 0. 1/2 times 2.7 times 8 squared. Okay, two significant digits, 86 meters.
So I have a question though, for like the acceleration you use, aren't you supposed to use the rounded version that you used?
I did.
It wasn't it 2.8 or?
2.7.
Oh, okay, never mind.
What am I missing on that answer?
Vector.
A vector. What is it? 48 degrees, right. If it's accelerating 48 degrees above the x-axis, that's the way its displacement is going to be too, okay? So sometimes people are like, God, I have to calculate vectors all the time. Nope, you calculate it once. It's the vector for the net force, it's the vector for the resulting acceleration, it's the vector for any resulting displacement, and any final velocity you might calculate, okay? So once you've calculated it, it applies to everything that's going to go after that, right? So it's still going to be at 48 degrees above x-axis. Okay, now I'll give you that break. I forgot about that part B. Okay. You know I said that car question was the easiest question you were going to get? I lied. This is the easiest question you'll ever get on Newton's second law. Okay, so I want you to write it down and give it a try. Lacrosse player exerts an average net horizontal force of 3 newtons forward on a 0.15 kilogram lacrosse ball while attempting to pass it. Calculate the average horizontal acceleration of the ball during the passing attempt. Okay, so think about what you're given. I don't think you even really need to draw a free body diagram here, in as much as they said the net force is. Okay. Okay, so for this one, as I said, we don't really need to draw a free body diagram. We're told what the net force is, and the whole point of a free body diagram is to identify the forces that contribute to the net force. So in this one, they told us what that is. They spoiled the whole thing. Okay, so 3.0 newtons forward. Okay, they also told us the mass of the ball, 0.15 kilograms. Okay, and they want to find the acceleration. So all we have to do is manipulate F net equals m times a for acceleration. So F net over m, so that'll be 3, all right, divided by 0.15, which should give us 20 meters per second, yeah? Meters per second squared, sorry, forward. Okay, as I said, that question's beneath you. I won't give you one that easy, okay? Because it's just too easy and it doesn't challenge you. Okay? Well, that's like saying, I always want to win, so I'm gonna go and, play football against kindergartners. Right? I'm probably always going to win, probably, unless they take out my knees, but. Okay, I want you guys to try, no, those are beneath you. Those are all too easy. Try this one. This one's a little bit more involved. Not a lot, but a little bit more. All right, so we got 2 athletes on a rowing team are training. Athlete A has a mass of 65 kilograms, athlete B 70 kilograms, and the canoe is 20 kilograms. Okay? Athlete A can exert a rowing force of 400 newtons forward, B 420 newtons forward, and in the water there is a resisting force of 380 newtons. So resisting means directly opposing or backwards. Okay? What is the acceleration of the canoe? So this is a lot like the pushing the car question. So let's have a look at this one. The trick with this one, as Tony pointed out, is that, or the mistake that people often make, is they assume that only the canoe is being accelerated. And so they write 20 on their free body diagram, and then they do all their math with a 20 kilogram mass. But the people are also in there, and their mass contributes to the mass that has to be accelerated. So yes, we do have to add all those masses together. So we got 135, 155 kilograms, okay, worth of canoe and people that have to be accelerated here. Okay? Our free body diagram is going to look like this. We have a 400 Newton force and a 420 Newton force that both act forwards. And then we have a resisting force of 380 newtons. Okay, so I've got my free body diagram, kind of like my givens. I'd get a mark for that. Okay, then I need to calculate the net force. Okay, because if I want to calculate acceleration, I have to have net force and mass. Right now I only have mass. So the other way to get net force, vector sum of all forces. Okay, so that's what I'm going to have to do. 400 plus 420 is 820 minus 380 is 460. 500. 4. So I shouldn't be math in my head. See? I'm not good at it. All right, 440 newtons is our net force. So our calculation there looks like this. 420 plus 400 minus 380, 440 newtons forward. Okay, so we've done that part. Now we can transfer that back up here to F net equals m times a. Acceleration will be 440 divided by 155 kilograms. Did I do that right? Because I did that one in my head too. Okay. All right. 440 divided by 155. Okay, so we've got an acceleration here to 2 significant digits of 2.8 meters per second squared forward. Okay, everybody all right with that? Okay. So again, the method is always going to be the same. We're going to do those 2 steps on every Newton's second law problem we do. What changes is the complexity of the vector sum of all forces part. Okay, that's going to get different. It's going to get more vector related. It's going to get, like, in some cases, almost mind-boggling. Okay, but we'll always be doing these 2 things. Right? Because a Newton's second law question is really going to ask you to calculate either acceleration or one of the contributing forces to the net force. So if you're given mass and acceleration and then told like 3 out of 4 forces, you're going to be looking for that missing force. So you go m times a to get the net force and then subtract all the other ones over to get the missing force. Or you get all the forces, you got to figure out their vector sum and find the acceleration. There's really only a couple of ways that that can go. Okay, give this one a try. This one, you have to read the question carefully. There's some extraneous information in this question. Right? Extraneous means stuff you don't need. Okay, so this question is like the physics version of a reading comp question. because there's some stuff in this question that doesn't matter. Okay, so it says in the men's 4-man bobsled event, the maximum mass of a bobsled with 2 riders, a pilot, and a brakeman is 630 kilograms. Well, whoop-de-doo. Okay, it actually doesn't matter for this question because in this question, not all 4 of them are in the sled. Only 2 of them are in the sled. That's why you have to read the question carefully. The next sentence goes on to say that during a practice run, riders A and B exert forces of 1,200 and 1,220 newtons each to accelerate a bobsled with this mass, 225 kilograms, a pilot, so the pilot's in it, 98 kilograms, the brakeman also in it, 97 kilograms. The other 2 aren't in it. They're pushing. Okay, so I actually have to add up those masses in order to figure out what mass is actually being accelerated here. Okay, so if you've ever seen the bobsled, okay, there's the pilot who's also usually quite strong, okay, and fast. There's a brakeman who's quite strong and fast because at the beginning, actually, all 4 are outside of the sled and pushing. And then as they jump in, they pop these handles down and jump in one at a time. The last 2 people are ballast. Okay, like they don't really have a job other than you have big, strong legs, so push. Okay, most of the people who do bobsled are people who were sprinters in track and field, but didn't have enough top speed to win, but they were very powerful. Okay, and they could accelerate very quickly. So they go into the bobsled where power is really important. Okay, so these guys are just pushing. The last 2 guys, they push and push and push, and then they hop in and go, okay, don't kill us on the way down the track. Okay, so the next sentence says they jump in for the challenging ride down the 1,300 meter course.
That doesn't matter.
Also doesn't matter, it's extraneous. Okay, during the pushing, the magnitude of the force of friction is 430 newtons. That's important. Okay, calculate the average acceleration. So we draw our free body diagram of the bobsled. Okay, and that bobsled is 225. Okay, 323 and 420, right? Okay. I always say I shouldn't do it in my head, and what do? Every question I try to do it in my head. Okay, so 420 kilograms. We have the pushers. Okay, 1,200 newtons and 1,220 newtons. And then friction, 430 newtons. All right, so now, from there, I know that I'm supposed to use this. Okay, but I don't have F net yet, but I can get F net through the vector sum of all forces, and it's going to be, so 1,200 and 1,220 is 2,420, so 1,990 newtons. I still haven't learned my lesson. 1,990 newtons. Okay, forward is my net force, just by adding those 3 things together. All right, then I'm going to divide that by the mass, which was 420 kilograms. That'll leave me with the acceleration, which will be 4.7 meters per second squared forward. Okay? The free body diagram, yes, that's your givens. You get a mark for it. Yeah. Okay? It becomes more important when we have to start drawing vector diagrams, then it's really useful for identifying the mean. Here, the forces were obvious, but we still draw it, just for practice. All right, so tomorrow, different, more complex situations. Same steps. Okay?